Yes. Sorry, like you would be yes, I can. No, so we know when we don't like I think what we divide it and use some basic I also I didn't see what if I said
Hello. The problem for our answer is correct. The process, you need to change something.
Well, but I cannot tell you now.
No, just the process. We calculate the distribution after that inequality and we calculate entropy and check for the useful solution for the
Yeah, you have to do this. Yeah. Well, if it's possible to do it analytically, the MATLAB, the numerical computation is not required because you have the analytic result. Okay, but if you want to also include some examples, well, that's okay. I mean, this would is also okay. You can do it like this, but the requirement was if you can do it analytically, you do
and
it
if not,
analytically. If not, you do it numerically. Okay.
okay, thank you.
You're welcome.
Per me anche è diverso, sono trasferito, diciamo.
Non torna
Probabilmente c'è un problema concettuale che forse avete calcolato vede che dice Peter Simbolo. Allora, se lei da questa parte di questi caratteri a 3 a 3, il risultato 3, che il numero di qui si trova per 3 caratteri. E quindi Probabilmente vi siete dimenticati di dire oppure c'è qualche errore. La logica che dirlo dovrei vedere sono qualche cosa. Perché non funziona mai niente, porca di quella zona.
But it's three. I think it's at least one. There's something like this. Something like I have one basically one record profile. Nice mind.
Buongiorno, sono il professor Parisco, sono nell'aula 11. Non riesco in inglese a far salire si chiama il piano
Lo sapevo, volevo sapere
Okay, good morning. Sorry for the delay. Can you hear me in the back? Can you hear me, please? Okay, I think that you should be able to hear me. So today we are going to finish the last part of the lessons, the last part of the theory, containing the parallel Gaussian sources. And then I will start to describe the second part of the assignment. Maybe you have already noticed that I uploaded the second part of the assignment on the Dropbox folder, so that you can use it, you can copy it, or whatever you prefer to do. And you can see that there are again 3 GUIs, like in the first part. The first one is for the calculation of differential entropy, numerical calculation of the differential entropy. The second and the third one are respectively for the implementation of the Lloyd algorithm and the LBG algorithm. And the last one are just 3 simple analytical calculations of differential entropy. So that concludes the second assignment. Before getting there, we have this last topic that is entitled parallel Gaussian sources. It may happen that a source is represented by a set of independent Gaussian random variables, xk, that have zero mean and variance is sigma squared k. And we want to encode each of these random variable separately by and obtain a corresponding encoded symbol that we call xk hat. And then we consider the quadratic distortion of this source that's given by the expectation of xk minus xk hat squared. And we want to satisfy this constraint that says that the sum of all the quadratic distortions is upper bounded by D. So the problem is how do we distribute the distortion among the different sources? In order to solve this problem, that's the first thing that we do is prove this inequality, the inequality that essentially says that the mutual information of a vector x of random variables and the corresponding encoded vector x hat is greater than or equal to the sum of the mutual information corresponding to each of the pairs xk, xk hat. And this is done by applying the conditioning inequality for differential entropy that says that the entropy of x given y is lower than or equal to the entropy of x, the differential entropy of x. We have seen this inequality for ordinary entropies. This inequality also holds for differential entropies and can be applied here to obtain this inequality here. That's exactly the inequality that we obtain taking this part and this part. Moreover, we use the fact that we have seen yesterday that the mutual information between xk and xk hat is given by 1/2 the logarithm in base 2 of sigma k square over dk if sigma k square over dk is greater than 1 or 0 if it is lower than 1. And therefore we use the notation that we have here, this plus here. That means that if you have any quantity A that you put in parentheses with a plus, this corresponds to writing the maximum between 0 and this quantity A. So if we write, there is a missing logarithm in base 2 in this expression. If we write the logarithm in base 2 of sigma k square over dk with the parenthesis and with the plus, that means the maximum between 0 and the logarithm in base 2 of sigma k square over dk. And this is what we have seen yesterday here, that the mutual information between x and x hat is 1/2 the logarithm in base 2 of sigma square over d when d is greater than sigma square. And if it is lower than or equal to sigma square, it's equal to 0. The mutual information is equal to 0 because the mutual information cannot become negative. So the problem, as we have seen before, is to distribute the allowed distortion d among the different sources. So we build a distortion function that is the sum of these terms that gives the overall distortion, and it depends on the different decay. And given the sigma k square and the constraint on the total distortion that is equal to capital D, the minimum set of distortion can be obtained, and it's given by this expression here, the minimum between an unknown parameter lambda, this is an unknown parameter that has to be found, the minimum between lambda and sigma k square. And so what we need to do to find lambda is solving this equation here. And since the minimum of lambda and sigma k square is lower than or equal to, because the minimum between two numbers a and b is obviously lower than or equal to a and also lower than or equal to b, so that if we take the minimum of lambda and sigma k squared, this minimum is lower than or sigma k squared, and so this sum is lower than or equal to the sum of the different sigma k square. So what we have to do in order to find our decay is to set the total distortion equal to this sum and to find lambda. And this can be done in a way that is very similar to the water filling algorithm. And this in particular is called a reverse water filling algorithm. Let's consider an example. In this example, the signal power sigma k square are given by 1, 2, and 3, and the total distortion is equal to 4. So we have to solve this equation, sum for k that goes from 1 to 3 of the minimum between lambda and sigma k square equal to 4. Let me write it this more explicitly. Minimum of lambda and sigma square 1 plus minimum of lambda and sigma square 2 plus minimum of lambda and sigma square 3 equal to 4. That's the equation that we want to solve. To solve this equation, we have to consider different possible values, different possible ranges for lambda. And the ranges are found by using the sigma squares. So we take the real axis for lambda. We start from 0, and then we put this first sigma square, that is 1, the second that is 2, and the last one that is 3. So we consider this range that is the first range, the second range, the third, and the last. 4 possible ranges for lambda. So first of all, we assume that lambda is lower than 1. If lambda is lower than 1, the minimum between lambda and sigma k square is always lambda, because lambda is smaller than 1, is smaller than 2, and is smaller than 3. And therefore, the equation becomes 3 lambda equal to 4, or 4 equal to 3 lambda. That gives lambda equal to 4/3. 4/3 is greater than 1, so this solution is not acceptable. Okay. Then we pass to the second interval. In the second interval, lambda is between 1 and 2. So since lambda it is greater than 1, the minimum between lambda and 1 will be 1. That is, the minimum between lambda and sigma square 1 is 1, whereas the minimum between lambda is sigma square 2 and lambda is sigma square 3 are both equal to lambda, because lambda is lower than sigma squared 2 and it's lower than sigma squared 3. So the equation to solve becomes 4 equal to 1 plus 2 lambda. Solving this equation gives lambda equal 3/2, and 3/2 is inside the interval that goes from 1 to 2. Therefore, this is a valid solution of this equation and gives the distortion distribution. The distortion distribution is d1 equal to 1 and d2 equal to d3 equal to 3/2. And you can easily check that the sum of d1, d2, and d3 is equal to 4 as it was required. This optimum distortion allocation algorithm is called reverse water filling. It finds application in audio and video coding in conjunction with other techniques like DCT, wavelength transform, subband decomposition, prediction, and motion compensation. All techniques that are used in video compression that are not going to be considered during the course, and it can be seen that the level corresponding to the lambda that we have found can be used to cut the levels provided by the different variances that are 1, 2, and 3. You can see that in the first case, sigma square 1 is 1 and it's lower than lambda, so we keep only this portion of water. In the other two cases, we keep a portion of water that is proportional to the lambda. And so what we obtain is that the sum of these three quantities of water gives the total distortion D. This is it. That's the concluding part of the theoretical lessons. Now we can pass to the description of the assignment. Okay, as I said before, in this assignment, there are 4 problems. In the second part of the assignment, there are 4 problems. The first one is relevant to the calculation of differential entropy. And so we are going to build a GUI for the differential entropy calculation. It is completely described by this slide. We have a probability density function that is reported in this form as a function that can be used by MATLAB to calculate integrals. Notice that we have these dots. The dots refer to element-wise division in this case, or element-wise exponentiation in this case. They are required because the function needs to be passed to a MATLAB function that is called integral. Integral requires a function that is applicable to a vector. And so for this reason, we have to use this notation with the dot slash dot raised to, and it's not required with the plus, but it's only required with the division, the multiplication, and the exponentiation. So this is a requirement that can be used to simplify the work because you ask the user to insert these dots. If one wishes, one can write instead of this expression like this, the expression 1 over x squared plus 1, and process the string, this string here, in order to replace every slash that appears here with a dot slash and every multiplication symbol with dot star and every exponential symbol with dot exponential. But it's actually, I think it's a minor thing. The second input that we have here is the range of the random variable, that in this case is from 0 to 10. The range is used to normalize the probability density function because, as you know well, the probability density function integrated over the range gives 1. And therefore, this must be taken into account since we do not want that the user provides the normalization factor. The normalization factor is calculated automatically by the user interface. The GUI produces two results. One is the differential entropy that is given by the expression that you know, minus the integral from a to b of fx of x log 2 of fx of x dx. And the other one is just a plot of the probability density function. The plot of the probability density function just gives the user an idea of its distribution. For example, in this case, the distribution has a mode in 0, a maximum in 0, and then it decreases from 0 to 10. We could have used a different range, for example, a symmetric range from -10 to 10, and in that case, we would have obtained a different result in terms of differential entropy. This GUI can be used also to verify the results of problem 4. The second problem is an implementation of the Lloyd algorithm. And here I reported two examples that we have already worked out in detail during the lessons. The probability density function is the first input, is a function of x. Oh, by the way, I forgot to tell you also before, I assumed implicitly that the probability density function is a function of x, and therefore this expression is just a function of x. It does not contain any other variable. And the same applies for the second problem, problem 2, where also in this case the probability density function is just a function of x. Again, we have a range. This time the problem is different, of course, from the previous problem. And in this case, we want to find the optimum quantization points. And here we specify the number of quantization points that we are looking for. The output is the optimum distortion and the optimum quantization points. There is one thing to notice here. And the thing is that in the problem that we solved during the lesson, we assumed that the range was from -infinity to infinity. Here, however, we assume that the range goes from -10 to 10. This is different in principle, but the difference from a numerical point of view is very limited because e to the minus 50 is an extremely low number, so that using this range or using the range -infinity to infinity essentially is almost the same thing. So this is, how can I say, an approximation of the result that we had in the lesson. And as you can see, the quantization points are the same. Here I provided two examples. The first one is with the two quantization points that we were able to calculate analytically, both the quantization points and the optimum distortion. And in the second example, we calculated it numerically. And here are the quantization points, and here is the optimum distortion that, if you want to check, corresponds to what we calculated in the lesson with 4 quantization points. Of course, this GUI must be able to work with any number of quantization points, so that we can put 2, 3, 4, 5, 6, etc. We can put any number of them. Problem number 3 is the implementation of the LBG algorithm for two-dimensional vectors. Therefore, this is a two-dimensional quantization vector. In this case, we have a probability density function depending on two variables. And we try to simplify the calculations by approximating the continuous probability density function with a probability distribution that has masses, that is probabilities, in correspondence of a square grid. What is a square grid? If I take, for example, this reference rectangle, I can divide this reference rectangle into a 4x4 grid in this way. Okay. That is, I take 4 points over the horizontal direction and 4 points over the vertical direction to cover the rectangle. And in a more precise way, we can say that the points have these coordinates. Xi equal to x sub 0 plus I over n multiplied by xn minus x0, and yj equal to y sub 0 plus j over n yn minus y0. I and j are integer number that go from 0 to capital N. In this case, we have to take into account that the algorithm doesn't always converge to the minimum distortion, because there may be multiple local minima. Therefore, to take into account this fact, we use a number of random initializations for the quantization points. And for each of these initializations, we apply the algorithm and obtain a local optimum. And we calculate the corresponding distortion, and we keep the local optimum that gives the minimum distortion within the set of initializations that we have considered. And in other words, we make many trials, we make many attempts at finding the optimum, and we obtain different values of distortion, and we keep the best one, that is the minimum distortion, and the quantization points that correspond to the minimum distortion. The output of this GUI is dual. There is a plot of the minimum distortion with respect to the trial number. Minimum interpreted the minimum of the trials that have been run up till this point. And I'm going to show you the graph so that you probably understand this a little bit better. And finally, when we have run all the trials that have been specified, we plot the optimum quantization points after having run the specified number of iterations. This is these are the contents of the GUI. The PDF is, in this case, this bivariate Gaussian distribution. We use a resolution 100. That means that we use 100 and actually 101 points in the horizontal direction and in the vertical direction. The range of X and Y is given by these four numbers. These are, in the previous notation, X0, X1, Xn, Y0, and Yn, and this is N. The number of quantization points is the next input parameter. Then we have a seed for the pseudo-random generation of the initial location of the quantization points. Then we have this parameter that represents the number of trials, that is the number of initialization of the initial quantization points that produce local optimum. And essentially, that's it for the input parameters. Then we have two outputs. well, actually 3 outputs. The optimum distortion after 10 trials, this 10 is this number. Then we have the plot of the distortion versus the trial number. You can see that it doesn't change very much. It doesn't change very much. It passes from 0.30594 to 0.30590 at the 6th trial. And you can see that it remains constant during the first 5 trials. That means that, for example, at the 2nd trial, we either obtain a distortion equal to this one or something that is bigger, because this is the plot of the minimum until this number of trials. So let me be more explicit. If we have a sequence of minimum like this, 1, 2, 1, 3, 0.5, the plot that we have here is the plot of the cumulative minimum. That is the plot of 1, because when we start, there is just one minimum, and the optimum minimum is 1. At the 2nd step, at the 2nd trial, we obtain 2, but 1 is better than 2, and so we plot 1. Then we have a 1, and we still plot 1. Then we have a 3, and we still plot 1, because 1 remains the best. When we find 0.5, since 0.5 is lower and therefore better than 1, we plot 0.5. And that's the way how we plot this cumulative minimum, because we want to see the behavior of the optimum distortion with respect to the trial number. And finally, we have this plot of the locations of the optimum quantization points. That, as you can see in this case, where we have a probability density function that is circularly symmetric, that is, if we rotated the surface representing the probability density function doesn't change, there is circular symmetry. We have one quantization point that is almost in the origin, approximately in the origin, and 6 quantization points that are almost located over a circle. Almost because this is not the optimum solution. It's a solution that is close to the optimum solution. The optimum solution would require that these points are exactly over a circumference, over a circle. Finally, problem 4 is consists of the calculation of these 3 differential entropies corresponding to 3 probability density functions. These are already normalized. In the sense that if you take the integral of any of these probability density function over the corresponding range, you obtain 1. The range is not specified explicitly because I used here the unit step function. With the unit step function, the first one has a range that is from A to B. The second one has a range that is from 0 to infinity. And the last one has again a range from 0 to infinity. This is implicit in the presence, from the presence of the unit step function here, 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 and also here. Oh, so this is it. You can start working on this, and or if you have any general question that you want to ask, I can also answer now. Otherwise, I'm going to answer the question to anyone specifically. Uh, There is one thing that I would like to tell you, and also I would like to record this, and it concerns assignment, the first part of the assignment, in particular problem 3. Concerning problem 3, some student asked me if it is okay. Is it okay to use a MATLAB function for the Hoffman code? I received this question a few times, and therefore I decided to give an answer and to put it on record so that everybody knows. Of course, everybody who looks at the recording or is present now. You can see that this problem has essentially two things. Find a probability distribution, find an entropy rate, and find the average number of bits per character. Okay? It doesn't say find the code. It doesn't. There is no place where it says find the code. So if you use a function that calculates the code, then you're using something that is not what is strictly required. Okay. Now, I already told you during the classes that to find the average number of bits per symbol in a Huffman code, you can use this function where you extract from a probability distribution the two smallest probabilities, and you calculate the function recursively by adding the sum of the two smallest probabilities to the function of the probability distribution where we have m-1 probabilities. The first one is the sum of these two probabilities, and the other ones remains the same. This function has the only burden to find what are the two minimum probabilities, and so it runs very quickly. So it is a little bit useless to resort to a MATLAB function that calculates the code. Probably in the end, you obtain the same result, but it's just a little bit like overkill, because this function does many things that are not requested. Of course, you can use it, but you risk that maybe you are not using the correct parameters, because when you use a MATLAB function, you're not always sure that you are giving the right parameters, and you obtain a result that is not the correct one. Of course, you can do this, you can check the results, but it's like doing the work twice. In my opinion, it's much better to implement a recursive function that does this thing. Once you have this probability distribution, you pass it to a very simple function that you can write in just 4 or 5 lines very quickly. Let's say 10 lines. It depends on how concise you are in your method programming. Let's say 10 lines. You have this function that is very quick. It's very simple to implement. And so I don't see why it can be advised to use a MATLAB function to calculate this thing. Because I explicitly didn't want to ask you to build the code to simplify the problem, to simplify the GUI, okay? But if you want to do it anyway, you can do it, but at your own risk. Because if it doesn't work, you obtain wrong results. There is also this result here that you may check. Of course, if it checks with this result, probably it should be correct with every other text. But I don't want that someone comes to me and tells me, well, it's not my fault if my results are incorrect because it's because of the MATLAB function. Because I cannot accept that due to the fact that I gave you a simple way to calculate the average number of bits per symbol. And if you decided not to use this, to follow this way, well, you can do it at your own risk. Okay, that's what I wanted to tell you.